Hey, welcome back to the lecture. In this lecture, let me cover function call and AAPCS standard. AAPCS stands for ARM Architecture Procedure Call Standard. Let's consider two functions here, function X and function Y. Function X is calling function Y. In this case, function X is called as caller and function Y is called as callee. The callee function, that is function Y, also receives four input arguments from the external world or from some other function. And the function Y also returns a data back to the caller. These terminologies, that is caller and callee, are used more oftenly in this standard. This is a document actually, you can get it online. This AAPCS standard describes procedure call standard used by the application binary interface for ARM architecture. You will understand why it is required. Let me explain in next slide. So very importantly, the AAPCS defines how subroutines can be separately written, separately compiled, and separately assembled to work together. It describes a contract between a calling routine and a called routine that defines obligations on the caller to create a program state in which the called routine may start to execute. Obligations on the called routine to preserve the program state of the caller across the call. The rights of the called routine to alter the program state of its caller. This standard acts as a rule or specification when multiple people are developing multiple assembly routines and all those assembly routines finally go into one single project. Then all must adhere to one specification. When a C compiler compiles code for the ARM architecture, it should follow the AAPCS specification to generate code which involves caller and callee. According to this standard, a C function can modify the registers R0, R1, R2, R3, R14, and PSR, and it's not the responsibility of the function to save these registers before any modification. For example, let's say there is a function Y. In this function, you want to modify R0 or R1 or R2, something like that. The caller has some important data in R0, R1, and R2, let's say. In function Y, you are modifying that. And caller needs that values after this function call to do some other job. But the function Y modifies that. So the specification says that it is not the job of the function Y to save these contents. That is the job of caller. The caller should push all these registers to the stack and after that pop it back when the function returns. That's what the standard says. I hope you get that point. If a function wants to make use of R4 to R11 registers, then it's the responsibility of the function to save its previous contents before modifying those registers and retrieve back before exiting the function. Let's say this function wants to modify R7. Then it first have to push R7, then modify R7, then pop R7 before exiting the function, so that when the control goes back to the caller, the R7 value must be intact. It should not be corrupted. These have to be followed if you are writing a function or a subroutine in pure assembly language. But if you are using C program, then you need not to worry at all. Why? Because compiler generates instructions. Compiler will follow these standards. A C program writer need not to worry about this. R0, R1, R2, R3, R12, R14 registers are called caller saved registers. It's the responsibility of the caller to save these registers on stack before calling the function if those values will still be needed after the function call, and retrieve it back once the called function returns. Register values that are not required after the function call don't have to be saved. R4 to R11 are called callee saved registers. The function or subroutine being called needs to make sure that contents of these registers will be unaltered before exiting the function. And remember that according to this standard, caller function uses R0, R1, R2, R3 registers to send input arguments to the callee function. The callee function uses registers R0 and R1 to send the result back to the caller function. Consider here a function, and this function x is calling function y, isn't it? When the function y is being called, 4 arguments are being passed to the function y, and the function y receives those arguments on its local variables. These are the local variables of function y. According to this standard, always these 4 registers are used to pass the arguments from one function to another during function call. What function x does is it copies these values into its internal registers R0, R1, R2, R3, and function y copies the register contents back to its local variables. That's how arguments being passed from one function to another during the function call. When this function y, if it wants to return the result, then it will always use the register R0. It copies the result to R0. If the result is 64 bits, then what happens is 2 registers being used, R0 and R1. So the higher 32 bits will go here and the lower 32 bits will go here. That's how result is returned back to the caller. But what if the arguments are more than 4? What if it is 5 or 6 or 10? Function y sends 6 arguments, and let's say there are 6 local variables to receive the arguments. In that case, 4 may be passed through the registers, and for the rest, stack will be used. So like that. First 4 arguments may be passed using the registers R0 to R3, and another 2 arguments may be passed through stack memory. But according to this standard, the input arguments will not be passed using R4 to R12 registers. Always R0 to R3 registers will be used for argument passing, and R0 and R1 will be used for return values. In the procedure call standard document, you can find all these details. You can go to the base procedure call standard machine registers, and you can see that here R0, R1, R2, R3. Only these registers are used for argument passing, and R0 and R1 are used for result, that is for the return values. R4 to R8 are used as variable registers. I mean, let's say in a function you want to create a local variable. So the memory for the local variable will be reserved in stack memory. To access that stack memory, always R4 to R8 registers are used. And even R10 and R11 are also used as variable registers. For this project, let's analyze the assembly instructions generated. For that, you can right-click on this project and go to its folder where the project is. The project name is stack. Let's get into that. Go to debug, and you can open the list file here. Oh, sorry, not that. Project name dot list. Just open that. This will give you all the assembly instructions generated for this project. Let's go to our main function, which is right here. Here we call function add, and for that branch instruction is used, branch with link to this function add. Before that, look at these assembly instructions. The arguments are populated in the registers R0, R1, R2, R3. That means these registers are being used to pass the arguments according to the standard. The compiler should always use these registers, remember that. And now let's go to the function add. Then there is a call function add. Let's go to the function add, which is right here. The function add has 4 local variables, int a, b, c, d. You can see that here there are store instructions. Data is copied from registers to stack. This is a stack manipulation. You can see that R7 is used as stack pointer here. Since R7 is a callee saved register, before modifying R7, the callee saves the content of R7. Again, this is as per the standard. Remember, the callee need not to worry about the contents of R0 to R3, but it should worry about the contents about R4 to R12. That's why it pushed the value of R7, because it is going to alter that here. All these are store operations. So values from the registers being copied into the stack, these are the places where these variables are created in the stack. After that, there is the addition. And after that, result is there in R3. This is the end of addition. And result is in R3, and that result is copied to R0, because that's the way a function should return the value back to the caller. That's the reason R3 is copied into R0. After that, there is a return from this function to the main function. In the next lecture, let's understand stack activities during interrupt and exception. I'll see you in the next lecture.